Good morning. Thanks for joining me today. Today we are going to talk about using FreeRTOS and in particular using FreeRTOS in IoT applications. Very specifically about how to achieve compatibility with and so then also certification for the PSA functional API. Before doing that, I always want to make sure that people are aware of what FreeRTOS is so they don't get to the end and wonder what I'm talking about. So I'm going to set the scene by talking a little bit about what FreeRTOS is, what we've been up to recently, then move on to IoT and how it fits in with the PSA before wrapping up very, very briefly with where we are going with this. So let's kick off with what FreeRTOS is. If it's not obvious, it's a free real-time operating system, to remove the acronym there. The real-time part kind of really denotes the class of operating system. So it means it's deterministic, designed to be deterministic. This FreeRTOS is generally built in devices that are placed in the environment, interact with the environment. And the real-time nature means that when it receives an input from the environment, you can calculate the kind of worst case before that input gets processed. As we will see, the FreeRTOS distribution contains a number of libraries, one of which is the kernel. The kernel is effectively a C library that implements multi-threading. Notice sometimes I say multi-threading, sometimes I say multitasking. When I do that, and it's a bad habit, but I'm talking about the same thing. Building that source code into your application then enables you to use the FreeRTOS API and then architect your system as a set of independent but communicating threads of execution. The chart on the screen now I've used in talks over many years, and it shows where FreeRTOS fits in the kind of continuum of processing power. Actually, before I move on to that, FreeRTOS has been ported to 40 different architectures, something like 20 different compilers. Getting it to compile without any warnings and that many compilers, some of which are 8-bit, some of which are for 64-bit. You can imagine the fun we've had with that. It also runs, in addition to those 40 different architectures, it also runs on Windows and it runs on Linux. Now, you are not going to get real-time behavior on those architectures, but they are very, very rich architectures for doing things like feature development, which doesn't actually require the real hardware. So most of the TCP/IP stack, for example, we've done on the Windows port. Also, if you just want to evaluate the code or you want to run unit tests or anything like that, then it's a very good environment. So this chart on the screen now is not those non-real-time environments. What I'm showing here is the blue is the FreeRTOS technology. The higher up the y-axis we are, the more applicable it is. The x-axis kind of shows the continuum of processing power. So on the very left-hand side, we're on very small architectures. Maybe you're not even using C code, you're just using assembly code. As you move along the x-axis, the processing power or the size of the RAM or whatever is getting greater. And you can see where FreeRTOS starts to go up. It typically is in the 8-bit space, but where the FreeRTOS going up crosses with the orange, which is no scheduler going down. That's where using multi-threading can be, it's very subjective of where the cross point is, but that's where it can be more beneficial than not. That's typically in the kind of Cortex M0 kind of space. If we go right to the edge of the x-axis there, then we are into the low-end Cortex A. If we go way, way, way off the scale, that's where you'll find the kind of 64-bit architectures. That's fewer use cases for FreeRTOS on those larger architectures, so I don't bother putting it in that scale. Also worth noting that FreeRTOS supports memory protection unit, but it doesn't support virtual memory. So it's like a flat address space. This diagram is showing the number of downloads over the last 18 years. You can see this has been going up over the years fairly consistently. It's downloaded about once every 170 seconds now. That was the average over 2019. These actually numbers undercount because most of these come from SourceForge, the SourceForge server where FreeRTOS was hosted for a very long time. It outdates Git and GitHub, of course. Where you see the blue turn to that kind of dark blue or black, that is where we actually switched to GitHub. And this is just another diagram which is showing the growth. This is actually views or unique viewers, however Google counts a unique viewer of the freertos.org site. It kind of creates a virtuous circle. The larger the community gets, the more ecosystem there is support, and then the larger the community gets. For example, I'm doing a talk tomorrow, I believe, with Wittgenstein that I'm introducing their talk. They've been a fantastic part of our community for ages. That talks about safe RTOS, which is a safety critical version. I'm also going to introduce some of the work that Amazon are doing as a huge contributor to the ecosystem now as well. I'll get onto that very shortly. What have we been up to recently? Then I'm showing on the, sorry, that was the download slide there. Well, I'm now moving on to what we've been up to recently. If we look on the left-hand side, that's just a screenshot from GitHub. The URL for the FreeRTOS organization in GitHub is there. That's been a huge success, actually. You can go and see all the activity. I think we've got contributions from like 6 or 7 different silicon vendors. Wish we'd done it a lot sooner. The right-hand side is a screenshot of the forums. Now, the forums used to be on SourceForge, but you can get FreeRTOS from many different places. So we have decided to move it directly onto the freertos.org site. Again, that's been a huge success. This is your opportunity as a FreeRTOS user to actually interact with the developers of FreeRTOS directly if you have any questions or you're struggling with anything. The reason I say that's been a huge success is because there's a growing number of community members who are also answering questions there. So this slide is showing some of the work we have done in the kernel itself, because it's not all about IoT. FreeRTOS users are many and varied application areas. This is showing some work we did recently to introduce a very efficient core-to-core transport mechanism. This allows asymmetric multiprocessing scenarios where you have FreeRTOS on multiple cores. All you need is shared RAM to do this. It's actually preferable if you are able to if you're able to have one core interrupt the other core as well, because then it can be a lot more efficient because you can make it event-driven. This next screenshot then is actually from a blog post which is on the freertos.org site. This is representing the work we've done with ARM v8m. So the FreeRTOS port for v8m has been around for quite a long time. We only kind of released it officially maybe about a year or so ago, because that's when we were getting users in there for real. We're getting more and more users on this port now, and they're giving us great feedback, so we're improving it. It's very flexible. It can build in or out trust zone support, memory protection support, all those different things. This next slide then is representing, this is actually a screenshot of all the different features being defaulted if you don't build them into your application. So every new feature we have is kind of backwards compatible by default. And this is just showing some of the additional work or the enhancements we've done to direct-to-task notifications in FreeRTOS. They were originally designed as a very efficient method of driver libraries interacting with tasks. If a task wants to start communications and then either wait to be notified that it's finished or be notified later that it's finished, the interrupt service routines can communicate with the task. Those use cases assumed that you weren't going to want them to maintain state across a function call, but now they're used in lots and lots of different scenarios. So we've enabled people to say how many task notifications they want, because previously there was just one per task. Okay, so we can't do a talk about FreeRTOS without also mentioning the huge and I would say very unselfish multiple contributions that are coming from Amazon's stewardship of FreeRTOS at the moment. I say unselfish because whilst AWS naturally have an interest in ensuring that the large number of FreeRTOS users, the large number of FreeRTOS devices that are connecting to AWS's IoT services can do so both as quickly as possible and as securely as possible, all the additional functionality and additional libraries that Amazon are providing are all licensed under the very liberal MIT license. That means, you can use them for any purpose you like. FreeRTOS users are massively in unconnected use cases, but also connecting to other cloud services. And I've mentioned some of the benefits in this slide already, so I'm not going to go over those again, but I do want to mention some of the bottom ones, which are less obvious. For example, on the right-hand side here, I've stolen a few screenshots from a blog on the freertos.org site written by the ARG. This is the automated reasoning group within Amazon. And these are kind of mathematical wizards, with brains the size of planets, and they're doing formal proofs of memory safety and thread safety on not just the kernel code, but also the other libraries as well. And these tests are being built up over time and are part of our CI now. Also, it's worth pointing out, because it's particularly for IoT, is that Amazon have a lot of experience, of course, securing their cloud services and looking after their cloud customers. And part of that is that they have teams who are handling reports of potential vulnerabilities, and they're managing investigations, performing any remedial work, and then pushing out any changes that are required. So that is all available to FreeRTOS users now as well. Okay, so this is a good introduction actually to what we are doing in the IoT space particularly. FreeRTOS is used in many different use cases, of course, and the big one now, the growing area, is IoT. This diagram represents a subset of the IoT-specific services that AWS provide. The left third, this hexagon, is the devices which are outside the cloud and connecting to the cloud. This is where you'll find the FreeRTOS devices. The right side represents the services that are actually running in the cloud. What you can't see on the device side yet, but is more obvious on the right side, is all the functionality that is just required for you to be able to connect in the first place. These are things that don't themselves add value to your product, but they have to be there in order for you to add value through the IoT. And to explain what I mean there, we can think about something like authentication. So authentication, when the device connects to the cloud, it has to make sure that it's connecting to the correct cloud, right? And likewise, when the cloud allows the device to connect to it, it has to make sure that device is authorized to connect to it. And also, once it's connected, what's it authorized to do? Which services can it access and how? So this means there's a lot of kind of infrastructure. First of all, there's the gateway, of course, then the base security with encryption at rest, encryption of data in flight. The fleet provisioning, if we're authenticating, that means that every device has to have a unique credential, typically a private key and certificate. So how can we provision those at scale? How can we audit them? How can we monitor them? How can we route data? This is all the functionality that the cloud providers give for you, because they're the experts in that, and that enables you to get your data to the right-hand side here as quickly and as securely as possible. Okay, so let's come on then to see how the same is true on the device side. Remembering, of course, that the device side is much smaller, and this creates a lot more challenges. This is a block diagram or layer diagram of an IoT reference integration. This is a pre-configured and pre-tested integration of everything you need to take care of that undifferentiating functionality for you. And if you go to the AWS organization in GitHub rather than the FreeRTOS organization, you will find a lot of these, each ported to a different hardware platform and qualified as functioning correctly. What we're looking at here is like the application writer's view, and we can also show here, I say that because I've kind of hidden the complexity in that middle bit that just says middleware libraries. But here we can also look at how we can use the multi-threading to add more ease of use. OTA is shown on this diagram. That's over-the-air updates if you want a new executable image on the device. Now, that's a fairly intricate piece of functionality. That has to, it's also a very critical piece of functionality. And it has, security, a lot of security aspects to that as well. What we're doing here, using the multi-threading, we can just run that in the background as in an agent or daemon task. That will then, download the new image for you. It will flash it. It will check the signature again to make sure that it's an authorized update and make sure that it is not being tampered with. Make sure it's not being corrupted, and that kind of all happens in the background. So if now we look inside that middleware block, you can see that undifferentiating functionality, which is analogous to what we were looking at in the cloud. In this case, we're just looking at a common use case of MQT over Wi-Fi, MQTT, which is a protocol often used in IoT over Wi-Fi. In there, you can see the TLS security protocol. This is the protocol that our web browsers use to authenticate the websites that we connect to in the same way that devices authenticate with the cloud. Because we need to authenticate, we also need to provision each device, and that customization, as I was talking about, get the unique certificates on there. That then has a kind of cascading effect that we need to manage those secrets. Like I say, normally private keys used for that authentication, which in turn leads to the need for secure storage, not forgetting to mention secure boot, and all these kind of cascading pieces of functionality. And what's interesting here is the size of that undifferentiating functionality is largely kind of fixed for each use case, MQTT over Wi-Fi here. And it will often dwarf the amount of functionality which is making your product be the product. Quite often here I would show a diagram of a light bulb just to kind of drive this home, where the functionality, maybe it's a very sophisticated light bulb part of some kind of, maybe it's a stage show set or something with all kind of lights and coordination. And if you were to look at the memory map, you'd see the amount of code to implement the light bulb is very small, and the rest of the memory map is taken up with this kind of undifferentiating functionality. Now, here I've highlighted the modules here, which have a kind of security impact, the secrets management. I mentioned that quite a few times, specifically with OTA, and highlighting the other ones now. And what we want to provide is a method of these components accessing these secrets and the other crypto operations they need to perform without the components ever actually seeing the keys. If that, so by which I mean, if the key was loaded into RAM before you've accessed it, then a malicious actor may be able to access it as well. We need a bit of hardware support here, like a secure element or a secure enclave or the trust zone M, in order for us to be able to perform these operations without exposing the keys. And we do that in FreeRTOS using an open API standard that's used across many different computing industries. I think even like desktop computers use this, which is called PKCS 11. That stands for Public Key Crypto Standard 11. It's basically a crypto API standard for operations involving asymmetric keys, random numbers, random number generation, hashing. But the key here is it's, excuse the pun, is it's all done through handles. It's not done through accessing the keys itself. Now, I was going to show a kind of, the PKCS 11. So PKCS 11 is a standard which is managed by Oasis, an independent body, and there's a header file with all the API functions in it. I was going to show that, but it was a bit out of context. So instead, I just showed a table that showed why we are using the PKCS 11 interface or the security operations that we're accessing, things like signing and verifying, storing and enumerating certificates, storage and management of keys, that kind of thing, and then the APIs which we are actually using. So that gives it a bit more context. Okay, so next then, how does this fit in with the PSA or the platform security architecture? So to get to that, I'm going to show how these APIs in the ARM PSA certified environment, specifically in a moment, I come to talk about TFM, which is the Trusted Firmware M, which implements the Secure Processing Environment, or SPE, as it's, the acronym is often used, for both ARM v8M, so Cortex-M33, Cortex-M23, as well as dual core scenarios where perhaps you have a core which is dedicated to provide those security services, and that's kind of locked down from the application. So TFM is ARM's Platform Security Architecture, or PSA, reference implementation. It aligns with the PSA Certified guidelines. PSA Certified being a framework, for securing connected devices. It maps out from analysis through assessment to certification. And this slide kind of shows that PSA story across the value chain, from like chips, operating systems, and actual devices themselves. Now you see here that FreeRTOS is underneath the middle block there. So we are going to dive into that block in more detail now. So this diagram is showing the non-secure processing environment on the left. This is the gray part, and the secure processing area on the right. So Trusted Firmware M implements the secure processing on the right. This is not only providing that secure processing environment. Let me explain a bit what I mean by that. It's providing services such as secure boot, a set of security services for runtime, secure storage, crypto attestation, and it does this using and providing secure partitions. So everything is kind of sandboxed from everything else. So you can have kind of mutually untrusted components in there, but the lack of trust is mitigated by the fact everything is locked down in this secure processing environment. That's what the TFM manages inside the blue and green areas there. So the interface provided by TFM between the secure and the non-secure world is not provided by PKCS 11, but the PSA functional API. So that then raises the question of how can a standard interface like PKCS interface with TFM? And ARM have helped enable this by providing a shim that maps the PKCS 11 calls to the PSA functional API. And this makes it very kind of transparent to the FreeRTOS user. Now, again, I was going to show the source file that performs this mapping, but I figured that was not that helpful because it's kind of out of context again. So again, I've opted just to show a table that shows this mapping. It's not a one-to-one mapping. You can see sometimes when we call a PKCS 11 function, it maps to more than one PSA function. And sometimes when we call a couple of PKCS 11 functions, it maps to kind of more than one PSA function. So let's have a look now at how that actually works in practice. Here we can see the kind of data paths in our code. We have the data from the cloud is coming through that secured socket. The socket is secured using TLS. Now, the TLS here is using the PKCS 11 interface to access the kind of crypto operations. Normally, then, if you were porting this to a secure element or a secure enclave or something like that, you would have to provide an implementation of those PKCS 11 APIs to actually talk to whatever hardware is available. So here what we're doing is we have, because of this mapping, we actually have an implementation. If I put it crudely, you have the implementation of the PKCS 11 APIs, which is using this shim. So the shim is the link between those PKCS 11 calls and the PSA functional API. So this makes FreeRTOS PSA functionally API certified. Okay, so if you want to play with this, then we have a couple of options. This again is a screenshot from a blog on the freertos.org site. You can go to freertos.org/blog. This is a blog post provided by ARM. It goes through some of the stuff that I've been going through myself here. And if you read through this, you'll find links to the actual source code. The source code is hosted in a Linaro Git repo, and that targets the Musca B1 board, which is a reference integration, a hardware reference integration from ARM as well. The other option you have then is to go to the device catalog, the AWS device catalog. The URL is on the screen there again. And there you can filter on FreeRTOS and you'll find all the reference integrations, or you can filter on Cypress. You'll find this, which is a reference integration on a PSOC standard secure microcontroller, or the whole board, the reference integrations for the whole board. And this is PSA Level 1 certified and PSA Functional API certified and AWS qualified reference integration. So you can see how all these layers kind of enable you to build multi-layered security really at scale. And whilst you're on the AWS website, you can also go and look at some of the other things that AWS are doing to help provision devices at scale. You can look at things like fleet provisioning by claim, fleet provisioning by trusted user, multi-account registration. These are all value add that AWS provide that enables you to get around the rather practical challenges of trying to provision all these devices at scale. Okay, so that's a good introduction to FreeRTOS, telling you about our work in IoT and also showing you how we can use FreeRTOS with the PSA APIs. What I'm going to do now is just wrap up with a few things about what we are doing now. Now, I've spoken a little bit now about some of the value add which Amazon are providing. We're talking about things like fleet provisioning, OTA, all these kind of things. But when you actually connect to Amazon, all those protocols are completely standard. So I kind of separated on the screen how between the standard protocols and the Amazon specific. So the standard ones, you can see things like PKCS 11, HTTP, MQTT. So what we've done and continue to do is separate out those protocols and refactor them to make sure that we can use them in a very wide set of applications, a very wide set of usage scenarios. And what you can do is go to the freertos.org organization in GitHub, and you'll find these in there kind of boiled down, completely refactored, so they're decoupled from everything. They're decoupled from FreeRTOS, they're decoupled from each other. They're boiled down to the base functionality, no requirement for threading at all, even. And then by doing that, and remember these libraries have the benefits of like the memory safety proofs in their CIs, etc., and it's all MIT licensed. And we're enabling all these different use cases that I'm showing across the bottom. So from one end, if you have a device in the field already, which is on maybe on an 8 or 16-bit device, there's no, it's using its own TCP/IP stack or one that we don't support natively. So you can bring in MQTT by itself. There's no even dependency on the TCP/IP stack. So you can take that device and just enable MQTT on there. In the kind of the middle of the scale, we have the traditional FreeRTOS use case. We've already spoken about the kind of agent scenario when we were talking about OTA. Well, we do the same thing with MQTT. If there's no threading, then you have to kind of keep calling the MQTT library. When we run it as an agent, everything is managed for you. And you just have a very, very simple interface. Subscribe to this topic, publish to this topic. And it's a subscribe publish protocol MQTT. So you get the benefit of the multi-threading and a hugely simplified experience. All the way to the other side where we have these complete reference integrations, as we were talking about before, like that PSOC 64 reference integration. So, all this work is there for you. So that is the last slide here. I'm going to just finish off by saying thank you very much for joining again. I hope you come and have a look at what we are doing in GitHub. You can try the code in the Windows or Linux environments if you don't have the hardware there. Hopefully, if you get any issues, you can come and get them sorted out on the support forums. That's forums.freertos.org. And then, once you've done something fantastic, hopefully then you can then come back to GitHub and contribute back. So we look forward to seeing you there.